What is a query hint? A query hint is something that's used to nudge the database engine's query optimizer to pick a different path. Query optimizer? Different path? What are you talking about? The previous video discussed what indexes are and how they can improve query performance by leaps and bounds. But it's important to understand that indexes are just one component of the database engine's overall process for servicing your query request. To discuss the entire process, we need to zoom out a little. Every database engine on the planet has an optimizer to assist in the handling of queries. Basically, it's the database engine's algorithm that attempts to take your declarative SQL query and transform it into the most efficient thing possible. For example, if your query joins three tables, there's no requirement that the first declared join be done first. It may be more favorable to start with the last join. Queries fundamentally are commutative operations, meaning that no matter which order you carry them out, the results will be the same. Commutative is the concept that 1 plus 2 is equal to 2 plus 1. For join statements, this is applicable. And just so you know, there are situations where the commutative principle does not apply. Simply put, the faster you can throw away rows of irrelevant data and shrink a given result set, the better. Perhaps an example is in order. Now imagine a query like this. Select book.title, author.name from book. Left outer join book_author on book.id equals book_author.bookfk. Left outer join author on author.id equal book_author.authorfk, where author.name equal Mark Polak. The database engine gets to choose the order it joins the tables. Now, if you joined all book entries with the book author table, you'd have an intermediate result set. It pretty much looks like any other table in that it has rows of data with a distinct set of columns. And if you're confused by this, go back to the video, What is a Cartesian Product? That intermediate result set is then joined with the author table, producing a final result set with a complete representation of the book-to-author relationship. And then the engine can filter on the author.name column. Now, in a database with 10 million books and 5 million authors, if you're visualizing a huge intermediate result set being put together to filter for one author, you'd be right. But what if the engine started with the author table? And before it entertains the first left outer join, it instead applied the query filter author.name equal Mark Polak. The entire author table would be shrunk down to a single row. In other words, 5 million authors flanged down to one. And even though this is a row of a table, in this context, this single row is an intermediate result set that's partially fulfilling the query. What if the database engine then takes that intermediate result set and does a left outer join with the book_author table? That too would naturally produce a relatively small secondary result set. After all, it's only looking for the instance of the book author table that references that one author. Finally, join that intermediate result set with the book table, and you can probably visualize a very fast result set. A result set that has the same result as the first way we talked about earlier in this video. Now do you see why the database engine wants to throw away rows as fast as possible to speed things up? The little algorithm that decided to change the order is what every database engine calls its optimizer. And with that basic understanding, it's not hard to imagine more complex and detailed queries. For example, what if you had multiple query filter criteria spread across the various tables? Simple filter criteria like AND clauses can scale easily. The optimizer could iterate across every filter criteria and apply each one to its respective table first in order to shrink down those tables into smaller intermediate result sets. From there, it could then start carrying out joins. Now, as a rule of thumb, you typically start with the smallest size table and join from there, but other factors can kick in. All of this to say that data optimizers are powerful and will look at your data and your query to pick the most efficient path. This is why it's so important to embed as much semantic information as possible into your database tables and to also grant the queries as much information as possible as well. It's possible to do stuff outside the database engine, but there's an inherent risk to that. For example, the query above could instead have been done like this. Select book.title, author.name from book, left outer join book author on book.id equal book author.bookfk. Left outer join author on author.id equal book author.authorfk. This is the same as before, but without the author.name where clause applied. Instead, this result set could be handed back to the application, and the application does the filtering. That would still produce the same results, but that would be a huge mistake. You're hiding from the database engine that you want to filter by author.name. If you share that additional criteria with the engine, it will avoid loading up 10 million rows times 5 million rows between the book and the author table. Instead, by giving the database engine all of your criteria, it can do a much more effective job of finding the answer. Sometimes we imagine getting back an intermediate result set and then wanting to let the user enter filter criteria in the UI. But managing such a ginormous intermediate result set is probably not the best idea. Instead, take the user's inputs, send them over the wire to the database, rerunning the query each time, and taking the results back to the UI. Even as each character is typed, the user enters M, the query is run. The user enters A, the query is run again. The user enters R and K, each time the query is run again. Now, even though this sounds worse, in truth, it will probably perform better. That's because you would remove any situation in which you're asking for the entire result set of all books and their authors being queried and sent over the wire. And if you institute a 500 millisecond delay before sending the user's currently typed filter over the wire, you would probably achieve a suitable balance between UI and database engine power. Lean into the optimizer and try not to outthink it. It probably knows more about the data than you. But we started this video talking about query hints. So what are they? Query hints are ways to nudge the database engine in a certain direction. For starters, query hints are database engine specific. Some are as simple as use this index instead of what you think you should use, or do not use this index even if you want to. There are other query hints for different database engines that instructs it on various ways of caching or bypassing caches. Some query hints are workarounds for current bugs, which means that at some point in the future, that query hint may no longer even have any effect. One thing should be clear, a query hint is a suggestion, not an ultimatum. You have to read the docs for your specific database engine to know how much force a given query hint has. That's why it's good to not overuse query hints. Instead of putting hints into too many queries and repeatedly attempting to override the optimizer, it's a better investment of your time and energy to build indexes that best serve your queries. It should be on rare occasion that you need to override the optimizer. In fact, the only time to consider query hints, if at all, should only be after you've rewritten a query, analyzed it, and inspected the indexes you developed to serve your needs. After all, the whole point of using a relational database is to gather information and structure it into the proper format, representing the semantics of your domain model. Also, the goal is to have properly normalized data such that the optimizer can properly throw away the right bits of data when filtering and joining. Which raises the question, what is normalized data?